Welcome to a brief overview of PET scans. So what is a PET scan? Many people have undergone PET scans and have heard of them, but very few people actually know what's going on behind the scenes. So starting with the acronym PET, PET stands for Positron Emission Tomography. Now, tomography is a kind of imaging technique where you take cross sections of a subject, in this case predominantly human subjects, and build up an array of images layer by layer to build an overall 3D look into the interior of an object. Now, positrons are a kind of particle, so it can be stated that PET scans are some sort of tomography technique that uses positron emission to create these layers of images. To delve into this deeper, we must discuss what exactly a positron is. And it turns out, what kind of particle is it? It is a kind of antimatter. Now, a positron is what's known as an anti-electron, or in other words, the antimatter equivalent of an electron. Now, an electron, typically depicted as an E-, has a well-defined mass and charge of 9.1 times 10 to the negative 31st kilograms and negative 1.6 times 10 to the negative 19th coulombs, respectively. Now, a positron is typically depicted as E+, and has the exact same mass as an electron, but, as you might anticipate with the plus, an opposite charge with the same magnitude. Now, the properties of antimatter and positrons that are relevant to PET scans are thus. When a particle of matter and its antimatter equivalent interact, they annihilate each other. And based on the conservation laws of mass and energy, their mass is converted entirely into energy. Specifically for an electron and a positron, 1.022 mega electron volts of energy. This energy takes the form of gamma radiation, and specifically 2 rays of gamma radiation, so as to conserve momentum. So they travel in opposite directions but have equal energy, therefore their net momentum is 0, which is the same as where we started. Now, how do we detect these gamma rays? Well, we can build a detector out of an array of scintillators which fluoresce when exposed to gamma radiation. Now, this fluorescence can be detected by a photomultiplier tube that can convert that fluorescent signal into an output voltage that can be read with various instruments. So we build an array of scintillators, an array of photomultiplier tubes, we can pick up exact locations of where gamma rays are incident onto these array of scintillators, and how much signal each photomultiplier tube is getting will tell us which specific scintillator and therefore which location gamma rays were incident on. So if we build a ring of these detectors, we can then look for these positron annihilation events. Now remember, positron annihilation create 2 gamma rays when they annihilate with an electron. So we're looking specifically for when 2 of our detectors go off at the exact same time. And we can imagine recording that by drawing a line between them. Now, this doesn't tell us much right now, as all we know is that somewhere along this line, a positron annihilation occurred. But if we start getting multiple points and multiple coincidences of these 2 detectors going off at the same time, we can start to build up a map, and where we see these lines overlap, we can say, hey, most likely this is where our positrons were located and where they annihilated. So now we must think, how do we get these positrons into a patient's body? Well, we can use radiopharmaceuticals like fluorodeoxyglucose, which has a fluorine 18 on it that radiates a positron after some amount of time. Now the body treats this molecule as if it were to treat glucose. So it distributes it throughout the body wherever it would distribute glucose, which a lot of areas of interest to doctors like cancers and abnormalities use a lot of glucose. So the end result is that we move a patient 1 increment at a time through this ring of scintillator and photomultiplier tube detectors. So we image each section of the body around 5 to 7 times typically to build up layer by layer a series of images that allow us to look at a 3-dimensional map of where glucose has been distributed throughout the body, and therefore where our radiopharmaceutical has been distributed. Doctors and physicians can look at this and identify key organs in the body where glucose is supposed to be sent, and can also identify abnormalities and locations where high levels of glucose are showing up that shouldn't be there. An example of this is this little black speck on this example PET scan that the arrow is pointing to, which would be a high probability of being a tumor if it weren't some other organ. Now, some miscellaneous facts about PET scans. Their spatial resolution is limited to around 5 millimeters. A typical PET scan machine will sell from $1.5 to $2.5 million, and an individual scan will cost around $1,000 to $1,600 to perform. Each scan will take around 30 minutes, during which the patient cannot move or risk the worsening of the PET scan spatial resolution if you're shaking around too much. And an individual PET scan will only subject a patient to around 8 millisieverts of radiation. Now, to put this into perspective, risk of causing cancer doesn't start until exposure reaches or exceeds around 50 millisieverts of exposure per year, and radiation poisoning doesn't start until you reach the single sievert levels of exposure. Now, some limitations of PET scans are that they can't accurately image around wherever the radiopharmaceutical was located within the body, and they can tell you where it is, but not really how it interacts with the tissues around it. To account for this, you can use other imaging techniques such as MRIs and CT scans in order to fill in the blanks. And typically when you get a PET scan, you'd get it in conjunction with one of these other imaging techniques so that you get information on where the radiopharmaceutical that you were injected with was located and how it's integrated into the surrounding tissues. Now, some applications of PET scans to close things off are in medical research, where you can use it to image how the brain, cardiovascular system, and muscle activity move glucose throughout the body. For example, this image is taken from a study that shows how glucose is distributed through the leg muscles of people before and after walking, and can also predominantly be used in oncology, the diagnosis, treatment, and prevention of cancer, where the figure on the right here shows how we can use PET scans to identify where an abnormality of abnormally high concentration of glucose is held within a patient's body. Thank you for listening.